The partially molten plume beneath the Yellowstone supervolcano may be even bigger than other estimates suggested. The plume may be surrounded by high levels of silicate rock and briny liquid. The Yellowstone volcano last erupted explosively 642,000 years ago. Beneath Yellowstone National Park lurks a partially molten plume rising from the Earth's mantle, fueling the park's famous geysers and hot springs, and causing the crust above to bulge and recede in response to its forces. Now researchers report that the source beneath the surface may be even more massive than previously thought. Using a new technique, they have created an image of the plume beneath Yellowstone showing the cyclone shape stretching at a 40-degree angle to the west at a depth of 200 miles for 400 miles east to west, as far as the new technique can reach. This study does not make any predictions about future eruptions, which the USGS Yellowstone Volcano Observatory notes are of very low probability in any given millennium, since they have been separated in the past by 800,000 and 660,000 years. When the Yellowstone supervolcano last erupted cataclysmically 640,000 years ago, it formed the Yellowstone caldera, a 30 by 50 mile crater. Smaller, non-explosive eruptions have happened since, the most recent about 70,000 years ago. Previous estimates of the plume have used seismic images, which measure the reflection of seismic waves from earthquakes off of different types of materials below the surface. They reached even deeper than the new images, to more than 400 miles down. The new method detects differences in electrical conductivity generated by the different types of rocks and minerals below Yellowstone National Park, which provides clues to what they are made of. Using supercomputers, the research team, led by Michael Zdeneff of the University of Utah in Salt Lake City, created images of the plume based on the electromagnetic measurements from 115 stations in Idaho, Montana and Wyoming. We see that there is a partially melted, conductive plume at great depths starting in the mantle, and going up, Zdeneff said. It's a completely different technique, completely different data, he added. It confirms that the plume is there, but it provides another view of the plume. The plume's high conductivity suggests it contains high levels of silicate rocks and perhaps briny water, he said. The observation that the high-conductivity plume is larger and angled differently than the one found with seismic imaging suggests that the plume of molten and partially molten rock may be surrounded by additional liquid including briny water, Zdeneff said. I think it's an important finding to have a new technique to corroborate the way that this hotspot is rising through the mantle, said Jake Loneston, USGS scientist in charge of the Yellowstone Volcano Observatory. He noted that the finding does not indicate that the plume of molten material is necessarily bigger than earlier seismic images indicated, but that the plume's sphere of influence extends further than could be seen by the other technique. You're looking at the effects of that plume but not necessarily the plume itself, he said. It doesn't have great effect on the actual risk from the much more shallow volcanic system, he added. While this plume provides the heat that ultimately reaches the surface, he said. With these new images, you're looking at something that's way below the actual magma chamber that's responsible for the eruptions. The new study will be published in an upcoming issue of the journal Geophysical Research Letters. The plume's high conductivity suggests it contains high levels of silicate rocks and perhaps briny water.